Right. So having seen how we calculate, how we introduce the source, the next thing that we have to find out is why are we doing all of this in the first place. Okay. So from an antenna designer point of view, how can we motivate an antenna designer to get interested in computational electromagnetics? So we said, okay, if the currents are not known on the surface of the antenna in a very general way, we need to solve Maxwell's equation, therefore we can get the current. Next question is, so what? Okay, once you get the currents, you can get A, from A you can get E and H. Okay. Any other aspect you can think of? Why should a antenna engineer care about CEM? The answer is on the slide. It's about the impedance of the antenna. So normally, I mean traditionally, what has the RF world and the antenna world are two different worlds, right? So you have some RF circuit which generates your signals and all, and you have an antenna. Now when you combine two different electrical elements, what will happen? There can be a mismatch of impedance, and because of mismatch of impedance, what will happen? Right. So all the power is not, I mean the optimal power is not dumped into the whatever load you want. Some of it gets reflected back, which is undesirable, right? So how do we know what is the impedance of the antenna, right? So let's have a look at that, and that's one of the major applications of CEM for antenna design, right? So in the transmitting mode, I'm going to draw the circuit equivalent of an antenna, right? So what is in, let's take the transmitting case. So you have some generator, okay, it has some impedance of its own, okay, Zg is the complex impedance. So this is what the RF engineer designs till and gives it to you. Now he says, okay, you connect your antenna to it, right? So we can think of this as a 2-port over here, and this is your antenna, right? So here is where these two worlds will meet, and this is your antenna, right? So it's sending out radiation like this, right? What is the circuit equivalent of this? It's very simple. So looking from either of, supposing I look from here, this whole thing can be replaced by yet another impedance, right? So this I can replace like this. So this generator remains here. I have some Zg, okay, this is my port A and B, right? So there is some some resistive part and some reactive part, okay. So the antenna has been replaced by this lumped parameter, and so this together is Za. So I need to find out what the Za is, otherwise how, so for optimal power transfer, what do I want? Zg is equal to Za conjugate, right? So for me to know that, I need to find out what Za is, right? I don't exactly know what Za is. And similar problem comes in the case of your receiving antenna, right? So receiving antenna is, I can just draw this. So here I will have some load, right? This is a load over here. This is my two antennas, terminals. This is my receiving case, okay. And the circuit equivalent will become ZL is the load across which I have connected it. What do you think will happen over here, across from here? What should I draw? What will be the equivalent? A voltage source, right? There is some voltage induced in the terminal. So I have some V, I should not do it like this. Some Vt is induced and Za remains the same. Okay, by usually by reciprocity, this is the same. Okay, is that fairly intuitive, right? Some voltage is induced across the antenna terminals. That voltage is falling across both the impedance of the antenna and the impedance of the load. How do you find ZA is the question. Using? So you mean using or doing a measurement?
No.
Huh.
If we will get the equivalent circuit for the antenna, it's very easy.
No, when you say, okay, how do we get the equivalent circuit? I've drawn a box which says ZA, but how do I know what the value of ZA is? That has to come from somewhere. Either it will come from measurement, okay, or it will come from where? It has to come some Maxwell's equations or some approximation or something of the sort. Where will it come from? Yeah, I've made it into lumped components, but I don't know the value of the lumped parameters. What should I put for the value of RA and XA? It should depend, for example, on the length of the antenna, all of the physical parameters of it. That means if all of these things are involved, Maxwell's equations are involved, boundary conditions are involved. So there is a large theory of approximations which are used to calculate these lumped parameters. It will assume sinusoidal current, it will assume linear current, all of these approximations are there which will give you some form of ZA. Okay. And I am not covering those theories. There is a lot of, one is called induced EMF method and so on, various methods are there. Okay. The point of this course is to tell you how to do it rigorously and exactly, with as little approximations as possible. That is the objective over here. Okay. So, main question is, what is ZA? That is the sort of $1 million question. Okay. And more so as you go towards more sophisticated technology, this becomes more important because you think of a 5G antenna array board, right? The antenna elements are all very complicated structures. So all your original approximations of a nice sinusoidal current, they are no longer valid. So you have to do this numerically, right? So that is the thing. Now based on what we have seen so far, so we have studied the Pocklington integral equation, right? How will I calculate this ZA? So what did we do? Just to remind you, we had, let's take this delta gap approximation, right? So delta gap was VA volts applied across a distance of delta, right? This length was some capital L, right? What did I do over here? I broke up this into segments and applied a method of moments over here on each of these segments. Okay. So end result after MOM, what is it that is known? I is known after I solve the integral equations. Okay, very good. What is ZA now? V? I is a function of space, right? I expanded I on a pulse basis along the length of the antenna. So now which I will I put? Near the source, right? So after solving, I will get ZA will be equal to this applied voltage. So basically what is the current and voltage at the input terminals? That is the impedance, right? So it is VA by I Z naught, right? So we can say that this coordinate over here is Z naught. Okay. So this is how your CEM is going to tell you what is, after you have done the calculation, what is the value of the input impedance over here. You cannot match the free space impedance. Yeah, you can't match that. No. I mean, you have your circuit impedance as, let's say, 50 ohms, 75 ohms, and then you have to match it over there. You can't match free space. Not all the radiation is going to go into free space. You live with that. Okay. So the procedure is clear. How do I calculate the input impedance? Okay.